far you have a case theory, how to make it a theory of gravity. So to make it a theory of gravity, you have to impose certain constraints such that the local translations become general coordinate transformation, and the local Lorentz transformation acts on the tangent bundle of space. So this is what we have to do. Standard constraints are as following. So you have to state, so basically your constraints should be such that this omega mu AB and F mu A, they are no longer independent gauge fields, they become dependent. So this then can be interpreted as a spin connection, and they should be dependent gauge field. And so that if I impose this constraint, so this is basically the Gaussian-less constraint, which will give the spin connection, the omega mu AB in terms of the other independent fields, and this will give the gauge field associated with spatial conformal transformation, so F mu A, in terms of the other gauge field. So these are the constraints that you need to impose.
So far there's no matter.
There's no matter. This is just gravity. Yeah. So yeah. So this will imply that these constraints will imply that the gauge will correspond to NA because omega mu and Ka because they need F mu A. They will not be independent, and they will be determined in terms of the other gauge fields because E mu A and B. So yeah. However, now if you start doing counting, you will see that the total number of offshore degrees of freedom will be 5. So you can do the counting. So you see E mu A. Okay, so you count the number of degrees of freedom and then subtract the gauge transformation. So E mu A is 4 into 460. And so I count the independent fields. So E mu A and B mu are the independent fields now. So it's 4 into 416, and this is 4, so 16 plus 420. And the symmetries are, you have general coordinate transformation and local coordinate transformation, and dilatation and special conformal transformation. If you subtract those, you will get 5.
So this RP vanishing is the same as dE plus omega wedge E equal to 0.
Right.
And the other one vanishing is the same as the equation of motion.
The other one vanishing basically means that this curvature will become a wide tensor.
Will become
will be interpreted as a wide tensor. So you have basically this other constraint, which is this so R mu A B E mu A equal to 0, which determines how F mu A is written in terms of the other independent gauge fields. Just means that if you write down everything in terms of the independent gauge field, this will be wide tensor. The wide tensor has this property that if you take the trace, it is 0. Right? So that's what it will be.
So why are there only 2 of the 4 are independent?
Okay. So in the end, you want to write down the theory of gravity, which has only metric. Okay. So far I have not introduced any matter fields. Okay. So E mu A, it will give you metric, right? So omega mu A will be the spin connection. Okay. So F mu A is another dependent gauge field. So B mu looks like it's an independent gauge field, but it has the same number of degrees of freedom as spatial conformal transformation, right? So essentially, it has a total offshore degree of freedom is 0. So B mu in the end actually will not appear in the action. So because of spatial conformal invariance, B mu will actually not appear in the action. So it is kind of it will just disappear. So everything will be given in terms of E mu A in the end. Right? That's why you want omega mu AB and F mu A to be dependent gauge fields rather than independent gauge fields.
So maybe it's question of which of the 2 equations solve for what? So the first equation solves for omega.
The first equation solves for omega.
And the second equation solves for F and
F.
Okay.
Yeah. So that those 2 equations. So the number of equations itself tells you what they will like. The number of equations if you count is equal to the number of components of omega, and the number of equations here is equal to the number of components of F mu A. So that's So this will solve for omega, and this will solve for F mu A.
And these are constant in the sense that these are equation of motion corresponding to E mu A and.
No, these are not equations of motion. These are constraints in the sense that they determine omega mu AB in terms of E mu A. In the same way as the spin connection should be determined in terms of.
Yeah, we haven't even seen the equation of motion.
No equation of motion. Yeah. So these are the constraints which will just tell you that omega mu AB and F mu A are dependent gauge fields and not independent. So So yeah, so the total number of degrees of partial degrees of freedom if you found becomes 5. However, if you want Poincare supergravity, at some point you will break conformal symmetries and get Poincare supergravity. So there the partial degrees of freedom is 6. The metric has 6 components. So here it is 5 components, and essentially it's because of scale invariance. So there's dilatation, gauge invariance is there, scale invariance is there. So because of that, this is 5. So in order to get a Poincare theory of supergravity, you need to introduce an additional scalar field, which would be like a compensator for the extra gauge invariance that you have. So it will be like a compensator for the scale invariance. So that extra scalar field you need to introduce and use that scalar field to break scale invariance, so that you have a pure Poincare supergravity with the 6 offset degrees of freedom.
So something that shifts under dilatations by a shift.
Something that shifts under dilatation. In fact, this scalar field we introduce, we have a y weight 1 on the scale transformations.
Like the overall scale factor.
Yeah, correct. So this is So then we can write on the conformal invariant action for the scalar field, and this scalar field that we introduced, coupled to conformal supergravity. So this is the invariant action for the scalar field, where this d mu phi is the covariant derivative for the scalar field. The scalar field transforms only under scale transformation, so this covariant derivative has only d mu. But d mu phi will transform under other transformations also, so d mu phi will have everything here. That's okay. And by construction, this is conformal invariant, because this d mu is the conformal covariant derivative. So this is conformal invariant by construction.
So this scalar field has a wrong sign kinetic term or not? This is not real. I mean, there's supposed to be some problem with wrong sign kinetic term for the conformal mode of an edge.
Wrong sign kinetic. Okay. So let me see it. Yeah.
We can exit the full screen.
So what is your signature? Mostly positive or negative?
Yeah, I think signature is mostly negative. Sorry, mostly positive. Mostly positive.
So then it's wrong side.
That's wrong sign. Yeah. Right. You should have everything in front of us in terms of the dependent as well as the independent gauge fields. So now if you write your dependent gauge fields in terms of the independent gauge fields, so this is what you will get for the Lagrangian.
So this scalar field is going to decouple from the balance.
Yes.
Right? So you don't care about the ghost. I mean, you don't
Yeah,
care
right.
about wrong sign.
This is just a compensator. So we use this to compensate for the loss of scale invariance. So
So you fix scale invariance.
we
by
fix
setting
scale
it to one.
invariance by setting this to some constant. Yeah. Right. So that is what we will do. Yeah. So that is so this scalar field we use to gauge fix the scale transformation by setting this to this constant, and which gives rise to maximum Poincare supergravity. So this is so this is how we go from conformal gravity to Poincare gravity by starting from conformal gravity to gauge theory and then imposing constraints to write down the spin connection and the mu as dependent gauge fields, and then introduce the scalar field as a compensator and use this to gauge the scale transformation.
And what was the Lagrangian in terms of all variables, please?
Lagrangian in terms of
When you wrote down the Lagrangian, did you write them down in terms of the original 4 sets of variables?
yes. So this is the action for the scalar field coupled to conformal supergravity.
And the other part?
Other part is there, so that we can write as a separate. For example, we can write down this term, which is conformal invariant.
And R mu A is built out of, it's like the curvature of omega.
Yeah. So here this is the white tensor R mu AB. So because this contains F mu A also, I mean, yeah, if you separate out the F mu A part, then it becomes a Riemann tensor. But otherwise, this is a white tensor. Okay, so this is just white tensor square, and this is also conformally invariant, and that can be added to the action. So you get Poincare gravity with high derivative functions in that case. Okay. But so this is the Weyl square term. But if you want to couple it to the scalar field also, you need and it maintains full conformal invariance. then you need at least two scalar fields. Because one scalar field has Weyl weight, so you cannot write down any combination of just one scalar field which is k invariant. Right? So you need at least two scalar fields such that you can take the ratio of these two scalar fields and you can add an arbitrary function of this ratio to this Weyl square term, and that will still be conformally invariant. Right? So something like this you can write down. So you will have two scalar fields coupled to conformal supergravity. One of them you use as a compensator, The other one will remain as a field here. You have one scalar field coupled to Poincare supergravity. Right? So that also you can. Okay. So this will give you Poincare supergravity with high derivative corrections. With non-trivial coupling to the scalar field. Sometimes, if you don't write the scalar field, you just add this term. Okay, you will have Poincare supergravity with high derivative corrections, which is just this Weyl square.
Oh, and where did you get the square root GR term from?
Square, oh, that is here, right? So here we got the square root. Yeah.
It came from the matter part.
Yeah, from the matter.
Matter part once you solve for it.
Yeah, that's correct.
So why do you do scalars?
Yeah, so if you want to add a non-trivial scalar coupling to this derivative term, so with just one scalar, you cannot write down a scale invariant term because that one scalar transforms the scale transformation. Okay, so you need at least two scalars so that you can write down something which is scale invariant. That's the ratio of these two scalars.
And suppose you didn't have this high derivative terminology.
Yeah.
The theory would still be well defined because it's square root GR term.
Yeah. So it's a
So the full action would just be the matter action.
Right.
I have a question. Your R contains also F and G, right?
Yes.
So when you say root GR, that R is also defined by this.
Right. So this R that appeared here is the Ricci scalar. So this R is not the contraction of that R.
It's not the Ricci scalar.
Yeah. So I think I should have mentioned the hat. This R with the hat. So this
Yes,
R,
defined by the full.
So this R that appears here is the Weyl tensor, whereas this R that appears here is the Ricci scalar.
This is exactly the Ricci.
This is exactly Ricci.
So at this stage, so you got the usual Einstein action
Yes.
By imposing some constraints on conformal gravity.
Right.
So there is also a theory in which you don't put these constraints and you get something bigger.
If you don't put the constraint, then you have a gauge theory. Then that's not pure gravity. Then the symmetries don't act on space-time. They are some internal symmetries, right? If you write on a gauge theory based on conformal algebra, then so the constraints are equal if you want to make a theory of gravity out of that gauge theory.
Yeah, what I'm trying to say is that in what way is the path integral of conformal gravity different then from the path integral of gravity? Because in the off-shell content of conformal gravity, is that the same as
The off-shell content of conformal gravity, the off-shell content of conformal gravity is phi, as I said here. So this extra scalar field you introduce, the extra scalar field you introduce, then you have 6 off-shell degrees of freedom, and this scalar field actually, you use it to compensate for the scale invariance and go to Poincare gravity. Right? So here,
but this scalar field you can just gauge fix to be something, right?
Yeah.
That's off-shell.
Yeah. So
Because you're gauge fixing, you're not solving for phi.
no, we are not solving for phi. Okay, so if you so basically your fields are this invariant phi. These are the independent fields. Of course, there is a d mu writing, but then so then you have the symmetries are GCP, local knowledge transmission, which you anyway want in your final theory, and then you have scale and special conformal transmission.
Okay.
Right? So yes. So now if you just count the number of degrees of freedom, count the components here and subtract the symmetries, you get 6. Right? So total number of off-shell degrees of freedom will be 6. Will be 6. Right? And you use this phi to gauge fix coupled to conformal gravity, then optional degree of freedom is the same as pure Poincare gravity.
Was this phi, this phi was not part of the original labels?
Yeah. So if you just write down, if you just write down conformal gravity, the number of optional degrees of freedom is not 5 but 6, not 6 but 5. So if you have this conformal gravity, then your independent gauge fields are mu and d mu, and then you have the scale invariance. Then this is, if you subtract, then you get optional degrees of freedom is 5. Right? But if you introduce this phi, then the optional degree of freedom is 6, which is the same as Poincare gravity, and this phi basically compensates for this scale.
So without introducing this phi, what would have been the Lagrangian for this scale?
Yeah, so the Lagrangian is this, the high derivative Lagrangian. This one. So this is the Lagrangian built out of only conformal gravity fields.
So this is like Weyl square, root
This is
g
the Weyl
times
square.
w square.
Right, root g times Weyl square.
Nice.
And with the phi, can you get any higher derivative correction?
Something like this.
But no, I mean
With a single phi.
with one phi,
Yeah.
could you get here? You're getting Weyl square.
Right.
But suppose I wanted Riemann square.
Uh,
With that phi thing, could I arrange to get Riemann square? You should be able to, right? Because in the end you've got just gravity.
right.
So just some kinetic term for phi.
Yeah.
High derivative kinetic.
High derivative kinetic, but you want to write down the conformal invariant kinetic term.
But in the end you're going to break that. So,
Yeah, in the end you are going to break that.
so that's what I wanted to understand. Is there,
Yes.
can you get every term that you could, every high derivative term that you could have got from gravity through this route? Or are there some constraints?
No, I think through this route, when we are writing down the conformally invariant action and then using this scalar field to compensate for the scale invariance, I don't think you can get any high derivative correction.
You can only get very specific terms.
Very specific kinds. And right, in the context of conformal gravity, this is what I can say. In like conformal supergravity, depending on kind of multiplets, I think people have constructed Weyl square, Gauss-Bonnet, and specific types of high
But
derivatives.
suppose something's not conformally invariant, can't we then add in some appropriate scalar coupling to make it conformal?
So you say that some arbitrary Riemann square, and can you
And
make it?
then try to fix the non-invariance by using the scale.
Like the view filter.
Right. It just feels odd that you've got two different ways of writing gravity. In one way of which you've got some constraints to corrections
Yeah.
that don't come about from the other way. It's not important.
Yeah. Okay. So so this is all about conformal gravity. I wanted to tell what the way. I mean, why is it important? I mean, you can write down the theory of Poincare gravity. You know, it's a Einstein-Hilbert term, and if you want to add high derivative terms, you just keep on adding high derivative terms. So why is this important? I think it's important because it is easy to generalize this to supergravity, and conformal supergravity is a technique. I mean, it's supersymmetric generalization of all these things that I told you, but it's a technique where you can write down theories of Poincare supergravity where symmetries are realized offset, and so that's one of the reasons of trying to understanding this way of approaching gravity. Right? So I don't know if there is any other technique where you can write down theory of Poincare supergravity where the symmetries are realized offset. Okay, so certainly this is one of the ways where you can approach writing down theory of Poincare supergravity where the symmetries are realized offset. Okay. So yeah.
The string field theory reduced to, and string field theory is another off-shell realization of gravity. Does it slow energy sector become conformal supergravity in some way or something else?
Yeah, so the low energy sector, low energy effective action, I don't know about string field theory, but low energy effective action of that you get from string theory, those are on shell, right?
But string field theory is off-shell.
That's off shell, yeah. Okay, it gives low energy theories which are off shell.
Yes.
Yeah, constraint is to conformal supergravity. Yeah. So you basically start just like you start from conformal algebra there. You start here with the superconformal algebra, and corresponding to each generator you introduce gauge fields and field strength. Okay, and then that's a gauge theory. Then you convert the gauge theory to theory of gravity by imposing constraints. Okay, so you need to impose similar constraints. So those are the kind of, those are the constraints that those will be the same bosonic constraints that you need to impose, but you also need to impose some fermionic constraints. Okay, which is where, and that constraint you need to impose so that the fermionic partner of the spatial conformal transformation gauge field. So there's a spatial supersymmetry in this superconformal algebra, which is a fermionic partner of the spatial conformal transformation. So corresponding to that, you have a gauge field, which is not the gravity node. So that also you need to make it dependent. So for that also you need to impose constraints. Right? So apart from those two constraints that I wrote down earlier, you need to also impose certain fermionic. You need to set some fermionic curvatures to also 0. Okay, so those constraints will make some gauge fields dependent and some gauge fields will be independent. Okay, but once you do that, you will realize that the total number of offset degrees of freedom of the gauge fields, fermionic and bosonic, they don't match. Okay, so for example, in n equal to 2, if you are doing, you will get 17 bosonic degrees of freedom and 16 fermionic degrees of freedom. So they are not matching. So in order to have the right number of degrees of freedom, you need to complete the field representation by adding certain matter fields and modifying the transformation rules simultaneously in such a way that the superconformal algebra closes off shell. Okay. So there is a standard procedure of doing this. You need to add matter fields and change the supersymmetry transformation rules in such a way that the supersymmetry algebra finally of the full field multiplet closes off shell.
Zero auxiliary fields.
Yeah.
So what you're saying is that the constraints you imposed were not covariant under your algebra. That's why you have the problem. Yeah.
Yeah, that's not the only problem. I said number of bosonic and fermionic degrees of freedom are also not matching.
But that was a consequence of the constraints, right?
Before the constraint also they were not matching. So before the constraint also they are not matching, and after you impose the constraint because you need to make certain gauge fields dependent, right? So that after that also it doesn't match.
I see. Wait, I just want to understand before not matching. Is this just a statement that there are different number of fermionic and bosonic generators in the circuit?
Different number of fermionic and bosonic generators. Yeah. So that's right.
Good.
Yeah.
So because for each generator you got a gauge field.
For each generator you get a gauge field, yes.
Okay, so you're saying that because there are not the number of bosonic and fermionic generators in the superconformal algebra are not equal, that's why this procedure gives you different off-shell degrees of freedom.
Yes. Yes.
Okay, fine. And then you say you put some constraints that doesn't. I see.
Yeah.
Okay.
Right. So you need to add this additional matter fields to have right number of bosonic and fermionic degrees of freedom, and also change the supersymmetry transformation rules in such a way that your supersymmetry algebra closes off shell. It becomes different from the supersymmetry algebra that you started with, which was the superconformal algebra. So it becomes different in the sense that your supersymmetry algebra, when you take delta Q, on the right hand side, you have some field dependent transformation also. So
before you impose the constraints, your supersymmetry algebra closed off shell.
Before we impose constraint, yeah, right.
Because more or less by definition.
Yeah, by definition, it will start from the superconformal algebra.
So
right.
it was the constraints that stopped, that broke that.
Right, constraints is what broke that. Yeah.
So you're saying you cannot find constraints that mesh well with the algebra.
You can find constraint, but you need to add this additional thing. Yeah. So your constraints also has changes because you start with some curvature, some supercovariant curvature, but when you start adding these matter fields, you're also changing your supersymmetry transformation. So the earlier definition of curvatures that you wrote down are not supercovariant. You need to add extra terms into the curvature to make it supercovariant. So finally, the constraints will be in terms of the supercovariant curvatures.
Just to make sure I understand this.
Yeah.
you know, if you take n equals 1 supersymmetry, global supersymmetry in 4 dimensions, you've got some off-shell formulation, and then you can impose a chirality condition, which is like d bar on phi is equal to 0, and this commutes with the transformations, because if d bar is phi is equal to 0, you act with the supersymmetry transformation, that continues to be true. You know, this respects supersymmetry. So that constraint commutes with the transformations and continues to give you an off-shell.
Right. That concept will basically give you a chiral supersymmetry.
Exactly. So you are saying that the analog of that was difficult to find, and that's what's causing all the trouble. Is this right?
Okay, so I mean here you can still find a chiral multiplet. Okay. Yeah.
But for the gravity sector,
Yeah.
it's hard to find constraints such that if you act on a constrained field and then you perform the symmetry transformation, it continues to be a constraint. That the supersymmetry and the constraints commute with each other.
Right.
That's what's difficult to find.
Right. So so you're saying, yeah, right. So the curvatures, yeah. So the constraints are basically, the constraints should under supersymmetry transformation, they should go into each other.
Yes.
Right. Yeah. So that's so before introducing this additional matter fields, yes.
Sorry, if I may, like I think like there's a difference between so there's one thing which is that we impose a chirality condition. There's another thing which is we add the auxiliary fields. We add the x, and so I'm not seeing the. I think the second thing is adding a constraint which is like chirality condition, I think, and the third is just adding this auxiliary fields. Isn't that right?
But I mean, I think he was saying that there was no solution without adding these auxiliary fields.
Yeah.
Like in n equals 1 supersymmetry, the auxiliary fields were just part of phi.
Yeah. So okay. So do you add extra super fields in the third step?
In the first step, no, we don't add extra super fields. These will be the component of the final Weyl multiplet that I'm making.
Yeah, so he's just adding components, optional components to the super fields. So in that sense, he's adding
Right. Yeah, I mean basically this this I can write it as a chiral superfield, a restricted chiral superfield. I can write this whole thing as a chiral superfield. So these are like the auxiliary fields that I'm adding to this chiral superfield.
I'm not understanding. If the auxiliary fields were not always there. Oh, I see. You're saying now you're writing some super multiple.
Right.
Fine.
So before
and
yeah.
So if you just wrote the whole thing in super space, those fields would always have been there.
Okay. So once I do this, then I can write this as a super field in a super space. Before that,
there was no such thing.
Yeah. Okay. So that's how you. I mean that's roughly the flowchart of how to get this multiplet, right? So using this method, so n equal to 2 Weyl multiplet was constructed, and also the n equal to 4 Weyl multiplet was constructed. So
why can't I write a most general superfield components and then impose constant to see what can survive?
no, you can do that. See, you can write a most general superfield, and if you're interested, you can write on a flat space multiplet, right? But here I'm interested in conformal supergravity, right? So there is an analog of the gravity multiplet that I should have, right? Which would contain the graviton and the gravity norm, right? So that's what I'm trying to find out. This is the Weyl multiplet, right? So how will you write down the Weyl? Suppose I ask you, write down the Weyl multiplet, which contains the graviton, right? So how will you write it down?
I don't know.
Yeah. So this is the way that it has been constructed. You start with a gauge theory from the superconformal algebra, and then the independent gauge fields are just gauge fields, which are realized on some tangent bundle of space-time. But if you want to realize that as also a space-time symmetry, you impose constraints, and then after you impose constraints, then also need to introduce additional matter fields so that bosonic and fermionic components also match, and at the same time change the transformation rules in such a way that the supersymmetry algebra closest offset. Right? So that is how what will give you this Weyl multiplet. Right? So this. So here I have written something in red and something in black. So the things that I have written in red are the gauge fields, are the independent gauge fields that survive the superconformal algebra after imposing constraints. There are other dependent gauge fields that I have not written down, which is basically omega mu a, the spin connection, f mu a, the k gauge field, and the phi mu I, which is the S supersymmetric gauge field. So those three gauge fields are dependent and can be written in terms of these independent gauge fields. And these black ones are the additional matter fields that you need to introduce to complete the formalism. So this is for n equal to 2, and this is for n equal to 4. And so the matter part auxiliary field that we need to introduce is slightly complicated here. So you have a doublet of scalars. So this ij index are your SU2 asymmetry index. So here ij runs over 1 and 2. So these are your SU2 index. Here ij will run over 1, 2, 3, 4. These are your SU4 index. And apart from that, you have an alpha index here. So this alpha runs from 1 to 2, and this is a doublet of scalar field. And this scalar field actually parameterizes a SU1, 1 slash E1 coset. Okay, so this is a phi alpha. So this is constraint. I mean, this is needed. I mean, in the end, so there is a spurious U1 here, and in the end, there is a one complex scalar field which is physical. But to write down the supersymmetric transformation law in a nice closed form, this was done. So instead of, so there's only one physical complex scalar, but just for so that one is able to write down the supersymmetric transformation law in closed form. So it was written, this complex scalar was written in terms of this coset scalar, and the complex scalar is just one representative of this SU1, 1 by U1 coset. Okay. So this is scalar in terms of which n equal to 4 y multiplet.
Sorry, what is the alpha index run over?
Yeah, alpha goes from 1 to 2. Okay, so this phi alpha basically parameterizes an SU1, 1 slash E1 coset. And a particular, yeah. Yes.
So eta alpha beta is just 1, 0, 0 minus 1? Or?
Eta alpha beta is just 1 minus 1.
The 1 minus 1, diagonal of 1 minus 1.
And yeah, so these are the fields. This dijkl, this dijkl is satisfies some reality condition, which is this pseudo real. So this is the condition that dijkl satisfies, this reality condition. Right. So yeah, so we can do some counting here and see how many off-shell Bosonic and harmonic degrees of freedom we have for n equal to 2 and n equal to 4. So n equal to 2, which is counting. So you just count the number of degrees of freedom, number of components. Is 4 into 4, 16, which is 4, which is 4, this is 4 into 3, 12, which is 6 into, this is antisymmetric in ij, so, and this is antisymmetric and anti-self-one in AP, so this is 6, this is 1, and then count the number of symmetries here, okay, and you just add them up and subtract both the things. You will get 24 Bosonic. For anything also you do the same thing. Sin UI and phi I, and these are the symmetries. So you add this up, and subtract. That also you get 24. So there are 24 plus 24 degrees of freedom for the n equal to 2 y multiplet. Okay. This is clear. Just count the number of components and the symmetries, and you subtract them. So there are. So you get 24 plus 24 degrees of freedom for the n equal to y multiplet. For n equal to 4, you do the same countings. Yeah, so you do the same counting. You just add this number of components and you subtract them for symmetries.
So this phi alpha is a nonlinear field. I mean, right? Phi 1 square plus phi 2 square is equal to 1.
Yeah, phi 1 mod phi 1 square plus mod phi 2 square is 1.
So number of components is
3. Yeah.
So it's a nonlinear realization of.
Yeah. So there is so actually the number of physical scalar field is complex scalar field, so that is true 2. But once we deal with this coset, so there is a spurious U1 that also comes in. So that yeah. So this once we gauge fix this spurious U1, so everything will be in terms of a complex scalar and not this coset scalar. is manageable in this coset scalar to write down all the supersymmetric transformation law and everything. So this is just a technical thing so that the supersymmetric transformation laws are written in a much simpler form. If you want to write down everything in terms of the physical complex scalar, it will look complicated. So yeah, so introduce this additional spurious U1 so that 3 minus 1 is 2. So in the end, that's the physical scalar.
Mu mu ij is the gauge field for SU4.
SU4.
SU6, yeah.
Yeah. Right. So this is so we have SU4. Okay. So if you just add this up and subtract the number of symmetries, so we get 128. And for the Fermi case also, you just count the number of degrees of freedom here and subtract the number of symmetries, you get 128. So it's n equal to 4 while multiplet this contains 128 plus 128 bosonic plus Fermi degrees of freedom. Okay. Yeah, so it's much more complicated than n equal to 2, which had only 24 plus 24 components.
Sorry,
Yeah.
so the I runs over 1 to 4.
1 to 4, yes.
So how is lambda I is 16?
So lambda I is so there is I runs from 1 to 3 4 and it's a Myron it's a chiral spinner.
Oh, you're not showing the spinner index.
Yeah, not from the spinner index. So 4 into 4 16. So it's a positive chirality spinner. Right, similar the same thing is here. So there are 4 spinner index that I have not shown. So this has 20, so it's in the 20 of SU4. This IIJK, they transmit in the 20 of SU4, and there are 4 spinner components, so that makes this 8.
So the lambda is just the usual field theory superpartners of the gauge fields. Is this right?
Field theory superpartner.
Are these the same fermions that would occur in just n equals 4 Young-Mills theory?
N equal to 4 Young-Mills. No, you mean to say the vector multiplet fermions?
Yeah.
No. So vector multiplet there's that's different. So vector multiplet n equal to 4 vector multiplet is also there, but that's not off shell. There's no off shell vector multiplet in n equal to 4.
No, but here you have a gauge field, right? An SO6 gauge field.
Yeah, right.
And therefore you have the superpartners of that gauge field.
Yeah, the superpartner of that gauge field is not lambda. Yes. So, for example, this lambda was not there in n equal to 2, but the SU2 gauge field was there. So I don't. Yeah.
So I don't think those are the kites. Kites are the superpartners, right? Because they should be in adjoint. Lambdas are in the fundamental of SU4.
Yeah. No, the chi's are also in the fundamental. No, this chi is in the 20. 20 is not the adjoint of SU4.
Yes, it's not adjoint because there's also a Q. I mean, like, okay, so you have a so the vector field the SU4 vector field is in the adjoint, but
right.
then you add the Q on it. Okay.
Okay,
so
you're saying the Q acting on the gauge field, SU4 gauge field will give you a chi. That's true. That will be there. Yes.
Actually, you can also get it depends on how you contract. I guess you get a mix of chi and lambda.
Right. So here also you in SU2 also the Q acting on SU4 will give you a chi, but it will be like epsilon bar I chi j. So so it's basically you're right. So this is in the adjoint. Here the chi is in the fundamental, right? So it's so 2 cross 2 will give you 3. Yeah. So here it is 4 cross 4 bar cross 4 bar cross 20 will have a 15. That's I think that is what you want to say, right?
Yeah, so you write down the supersymmetric transformations relate these at some point?
Oh, so this was a very long expression, so if you want I can show you the supersymmetric transformation. Yeah.
Okay, yeah.
Do you want, I can find it out and show it to you. I looked at the paper, we can do the paper. Yeah. Right, so Yeah, so this is the n equal to 4 Weyl multiplet, which has this many bosonic and fermionic degree of freedom. Okay, so that's how the Weyl multiplet are constructed. And then what about an invariant action, meaning the supersymmetric generalization? So we have not yet introduced matter multiplet here. So suppose I want to write down an invariant action, how do I do this? Okay, for pure, let's say, Weyl multiplet, which should the supersymmetric generalization of the Weyl square term. Okay, for n equal to 2, there was a standard method which was known as the chiral density formula. So where you can take the fields appearing in the n equal to 2 Weyl multiplet.
Sorry, just one
Yeah.
question. So I've got a rough sense now for the gauge fields and and some of the fermions. But the scalars, how do I, in the n equals 4, what should I think? Where are the scalars? And only 3, yeah.
There are 2 actually. The physical scalars are 2, so 3 minus 1. So actually there is one complex scalar.
And should I think of them as transforming under the gauge transform? These are neutral under the gauge transformations?
These are neutral under the gauge transformations. Yes.
Nice.
Right. They don't have any Weyl weight. They don't have transform under SU4. They don't transform under anything. These are neutral under gauge transformations.
Okay.
I'm confused about the non-linearity of this phi thing. So this phi is belong to some S3 or something.
SU1, 1.
Well, it has phi 1 mod square plus phi 2 mod square equal to 1.
Yeah, so I had phi 1 plus phi 2 is equal to 1. So where
This is a non-linear constraint, right?
yeah, so where basically phi 1 is phi 1 star, whereas phi 2 is minus phi 2 star.
I see. Okay.
Mod phi 1 square minus mod phi 2 square.
Okay. So it's some kind of is analytically continuous string.
Yeah, it's SU11. Instead of SU2, it is SU11.
Okay, alright. So now, is this normal to have non-linear fields as
Right,
participating in?
Yeah, because supersymmetric transformation is highly nonlinear. In n equal to 4, the supersymmetric transformation is highly nonlinear. So, yeah, so if you express everything in terms of, now if you express everything in terms of a physical complex scalar, it will look extremely nonlinear. And,
I see.
yeah.
So you bring back the extra field which is dependent on the remaining. So you're writing everything in terms of this linear thing with a constraint.
Yes, yes.
And
Yeah.
I see.
Yes. I'm writing down everything in terms of phi alpha. The supersymmetric transformation will be given in terms of phi alpha because it's easier to write down in terms of phi alpha.
And the constraint is preserved somehow throughout.
Yeah. That's no problem with the constraint. Yes.
So one more question about this phi.
Yes.
So maybe this is jumping ahead. But if you let's say like couple this conformal supergravity to n equal to 4 superangle theory, a different n equal to 4 superangle theory. Right. So how will these phi's couple? Like what part of the n equal to 4 theory will this couple to? The Young's theory will this couple to?
What part?
Yeah, for example, v mu ij will couple to the SU4 part of the n equal to 4 Young's theory.
Yeah, I mean, it will couple. I mean, there is one action written down where n equal to 4 superangles coupled to conformal supergravity, and that is known. And so yeah, it appears as some coupling, but exactly I don't know how to say how it appears. But phi 1.
But it can't be some linear coupling because linear phi carries an alpha index, and I don't know anything in the n equal to 4
yeah, the way
this
the-
theory will
yeah.
get.
Yeah, the way this n equal to 4 action was written down by Deru, it was written, I will tell you the paper, but the way this coupling appeared was they wrote it down explicitly in terms of this phi 1, phi 2. So they didn't have an alpha index. So they wrote it down in terms of phi 1, phi 2 and all these things. So still the SU11 invariance is there, okay, but they didn't write it explicitly in terms of this alpha index.
But it can't. I mean, I'm saying there can't be a linear coupling. Am I right?
Yeah, it was no. There is a linear coupling. Yeah, there is linear continuity is there. Because the SU actually the vector multiplet, so this phi alpha transforms under SU11, and under this same SU11 the vector multiplet field strength also transform, that this so there is a field strength of vector multiplet and its dual that transforms under this SU11.
It's S duality.
Yeah, yeah, right.
Sorry, again, what?
So the vector multiplet has a field strength. There's a vector field and there's a field strength associated with that. And so
Yes.
the field strength and its dual, if
I think it's Hodge dual.
yes.
Uh-huh.
That transforms under this SU11. So you can write down some combination of this phi alpha and the field strength such that they are SU11 invariant.
Right. Okay. So hence the comment that this is related to the SL2Z kind of
Yes.
the duality kind of transfer.
Yes.
Interesting. Okay.
Yeah. Right. So this has this many family and bosonic degrees of freedom. Okay. For n equal to 2, what I was saying is how to write down invariant action. Is by writing down a chiral multiplet out of this n equal to 2 y multiplet. So basically, this is if you write this down. So this form A, psi, B, F, I, and C. They form the component of chiral multiplet. Okay, and they transform these things. One can check from the transformation rules of the Weyl multiplet that these objects actually transform like the components of the chiral multiplet. And in terms of right, and so they form a chiral superfield which is this WABIJ, and you can contract the SU2 and the Lorentz index and write down another chiral multiplet called the W square, and this is a so since WABIJ was the chiral multiplet, W square is also chiral multiplet whose highest component C, which is given in terms of this, basically we just have TAB, so F, and you have BB, so these are the, and then your psi bar chi, and then you have AC, so when you multiply this multiplet with itself, the highest component will come when A multiplies with C, I multiplies with lambda, B multiplies with itself, and F multiplies with itself. That is when you get the highest component of this W square chiral multiplet, and this has also Weyl weight 4. Okay, so so the good thing about n equal to 2 was that there was a density formula that was developed by these people, which is known as the chiral density formula, which is like if you have a chiral multiplet in the background of conformal supergravity, you can immediately write down an invariant action from the components of the chiral multiplet. And so everything, in order to write out any invariant action, it was important to embed that particular multiplet into the chiral multiplet, right? So that is what was done. So this is like embedding the Weyl multiplet into the chiral multiplet. You write down the chiral multiplet from the components of the Weyl multiplet. And once you have that, then you just plug it into the density formula that was developed by these people.
So,
yes.
So can you just tell me how do you define the chiral multiplet? Like what indices does it have in the superspace? I mean, like what are the chirality conditions?
Okay, so yes. Okay, so I don't have it's a chiral superfield. So it has a chirality condition. It's like d bar phi equal to 0. The same thing is there. But here it's actually, if you see, it's a restricted chiral multiplet in the sense that these components of the chiral multiplet fields are not independent, they are dependent, they are defined even in terms of the derivatives of the lower components. For example, CABIJ is given.
Maybe I'm asking a very limited question.
Yeah.
So this is a chiral multiplet in n equal to 2 superspace or n equal to 1?
N equal to 2 superspace, yes.
Yes, so it's in n equal to 2 superspace, and the chirality condition is what? Is the d bar with so d bar has an index.
Yeah, d bar alpha I. So if you so I don't know exactly how to write it down. I don't remember it, but something like this, right? D bar alpha I phi basically this means that the lowest component of the chiral multiplet transforms. So if there is this chiral superfield, there is the lowest component which will transform as delta phi will transform something like epsilon bar I. There will be no in the transformation law. There will be no epsilon bar lower I. In terms of components, I understand that the lowest component, in the transformation law, there will be only epsilon bar upper I, no epsilon lower I. That is my understanding of the chiral multiplet in terms of components.
If you just do a counting here,
Yeah.
so n equals 2 would ordinarily have had what 8 thetas.
N equal to 2 will have 8 thetas. Yes.
Yeah, this condition throws away 4 of them.
Yes.
Roughly speaking. So the counting would suggest that there are 16 components in a chiral scalar.
Yeah.
And how many components were there?
Okay, 16, but a normal chiral multiplet will have 16 components, 16 plus 16. But this is a restricted chiral multiplet.
And how many components were there in your
Okay.
multiplet?
Okay, so typically a restricted chiral multiplet will have 8 plus 8, but here this also carries this Lorentz index and the SU2 index. Right, so there is right, so this is a chiral multiplet which is WABIJ. Right, so this will have 8 plus 8 components, but this has ABIJ. So so this is like having this many number of chiral multiplets.
Sorry, so Bindusar, your phi carries some indices that you're not writing down?
Which phi?
On the blackboard, I think.
Oh, this phi. Okay. Yeah. So I have just been very schematic. The thing I wanted to say is that the lowest component of this chiral multiplet will transform into something which has only one chirality of epsilon.
Yeah. What is the index structure of the capital phi?
Oh, okay. So chiral multiplet, generally chiral multiplet will have a scalar field, will have a gauge field. Okay, so chiral multiplet, I think there will be a scalar field, there will be a gauge field.
I think he's asking if you just take the lowest component of that phi, what are those indices? How many chiral multiplets are there?
This is one chiral superfield. Right? I wrote this as a component. This is the chiral superfield. These are the components of this chiral superfield.
But there isn't an IJ index or anything like that.
No. A typical chiral multiplet has no SU2 or Lorentz index. So this is a chiral multiplet which carries this SU2 and Lorentz index. So these are that many number of chiral multiplets.
So your chiral multiplets will carry the SU2 indices.
Yes. Okay. Yeah. Also the Lorentz index. So there will be phi AB. Right. Yeah. So this is WABIJ basically.
So it's plenty of chiral multiplets, and that will account for the degree.
Yeah.
So for WABIJ,
Yeah.
So IJ is like, so this is in bifundamental?
So you can typically forget about this IJ because this is antisymmetric in IJ and you are in SU2. So antisymmetric in IJ in SU2 means it's a SU2 scalar, right?
Okay.
So you can forget about this IJ part. You can always contract with S1 and IJ and get rid of the IJ. So it's mainly carrying a Lorentz index. So it's a chiral superfield carrying a Lorentz index.
And it's antisymmetric in AB also?
It's antisymmetric in AB, yes.
Okay. So it's a two-form, basically it's a two-form chiral multiplet.
Two-form chiral multiplet, yeah, right.
Okay.
So that has 6 components.
Yeah.
So the total number of components is 6 into 16.
6 into 8 plus 8. It's a restricted chiral multiplet also. There's the
Yeah,
restriction.
so I'm saying before restriction, the 6 into 16 goes on again for me, and then you put.
Right.
Okay.
Right. So this is the way the invariant action was written down. You have this chiral multiplet constructed out of the Weyl multiplet, and you just put it into this invariant density formula, and you get the action for the n equal to 1 supergravity made purely out of the Weyl multiplet field. Okay. And you obtain the supersymmetrization of the pure Weyl square term in this way. Okay. So
And roughly the supersymmetric action is integral of d4 theta
d4 theta.
of your chiral multiplet.
Right. Yeah. So this construction tells you how to obtain the pure Weyl square supersymmetrization of the pure Weyl square term. Okay. But in order Poincare gravity, you need to introduce something analogous to the scalar field that we introduced in the case of the bosonic case. So there we introduced a scalar field which needed to compensate for the loss of scale invariance. So here also you need to introduce a compensator multiplet to gauge fix the additional symmetries. So the vector multiplet, for example, in n equal to 2 plays the role of compensator multiplet. So it is this analog to the scalar field that I introduced earlier. Okay. So this vector multiplet can compensate only for the dilatation and the S gauge symmetry. So there is S supersymmetry and the scale symmetry. So the vector multiplet has fields which can compensate for only this dilatation and the S gauge symmetry, but it will not compensate for the SU to R symmetry. So if you want your Poincare gravity to have the SU to R symmetry also, then it is fine. But if you want to obtain Poincare gravity where the SU to R symmetry is also broken, you need to introduce another multiplet which will compensate for the SU to R symmetry, and that typically can be a hypermultiplet, a nonlinear multiplet, or a tensor multiplet. There are 3 multiplet which you can use to compensate for the SU to R symmetry. Okay, so this vector multiplet has 8 plus 8 optional degrees of freedom. The tensor multiplet, nonlinear multiplet, or hypermultiplet also has 8 plus 8 optional degrees of freedom. So finally, your Poincare gravity will have 40 plus 40. So the Weyl multiplet has 24 plus 24, and the 2 compensator multiplet has 8 plus 8 and 8 plus 8. So your Poincare gravity will be defined in terms of fields which are 40 plus 40 offset degrees of freedom. So the Poincare gravity multiplet will be 40 plus 40. Okay, and you can you use this compensator to write down your action of Poincare supergravity where the supersymmetries are realized offset. Okay, so in this way you can get your Poincare gravity where the supersymmetries are realized offset.
So the most general Poincare gravity is something that you want a particular, not all terms you can generate by this one.
Yeah, so high derivative terms, not all high derivative terms you cannot find out the superconformation of all, but all types of Riemann square term. Right? So here, for example, the high derivative term you need to add this term which is the superconformation of the pure Weyl square term that we introduced, and so you will get superconformation of Weyl square term. There are ways also where you can get superconformation from Gauss Bonnet term. Okay, but there is no way you can generate all Riemann square terms. Okay. Although in 5 dimension there is a different construction of the Weyl multiplet, I think, where they have found out the superconformation of all curvature square term. So there's something called the dilatant Weyl multiplet, and you can use that to find out the superconformation of all curvature square term. That's there in 5 dimension. In 4 dimension, we don't yet have such a construction. Okay. Okay. So now let me move to n equal to 4. Okay. So what about n equal to 4? So what I discussed here in the previous slide was how to do this in n equal to 2. So n equal to 4. It's interesting because it's the maximal n in 4 dimension when an offset formulation is possible. In n equal to 8, you don't have an offset formulation. N equal to 4, you have an offset formulation where the Weyl multiplet is still realized offset. The vector multiplets are realized onset, but at least you have the Weyl multiplet which is realized offset. So you cannot, for example, write down the theory of Poincare gravity in n equal to 4, which is offset, but you can write down the theory of conformal supergravity, which is offset.
Can you
for example, the vector multiplet is onset in n equal to 4. You cannot write down the offset vector multiplet in n equal to 4.
So you cannot write down now, you cannot write down ever.
You can write down, but you need to introduce infinite degrees of freedom. It's the same story for hypermultiplet in n equal to 2. For n equal to 2 hypermultiplet, you can write down an off-shell hypermultiplet, but then you need to add infinite number of fields. Okay, so perhaps in n equal to 4 vector multiplet also you can do that, but if you want to restrict yourself to a finite number of components, then the n equal to 4 vector multiplet is on-shell. So yeah, so that means that you cannot write down the theory of Poincare supergravity in n equal to 4, which is off-shell, but you can write down the conformal supergravity in n equal to 4, which is off-shell. The only known off-shell multiplet in n equal to 4 is the 128 plus 128. Okay, so that is why this is interesting, because this maximal end where an offshell formulation is possible, and at this presence of these quotient scalars, this phi alpha that I told you before, this also poses challenges, and also this is the last unknown action in that was not known. So that is, yeah. So that is why this is interesting.
You're saying the others just don't exist.
Which,
Like let's say n equals 8.
n equal to 8, there's no offshell formulation. So it doesn't.
So I have the same question. Like,
Yeah.
how are these things known? I mean, these are like no-go theorems, or these are the current state of knowledge?
Okay, so yeah, so n equal to 8, I think there is some argument which I think Bernard and people made in the 80s. So n equal to 8 also, if you want to make it offshell, I think you need to add infinite number of degrees of freedom, which
But you know, once again from string field theory,
yeah.
Ashok had a slightly unusual kind of action.
Uh-huh.
You know, there are all these theorems that can just type 2b, for instance, does not have an off-shell formulation with a finite number of fields. But Ashok had a very simple counterexample to that. Do you remember? We talked about it a year or two. This business, it had an additional free scalar field, which decoupled from everything else. So technically it wasn't. I mean, I am a bit suspicious of the statement that there isn't an off-shell formulation of n equals 8, because string theory in flat space gives you n equals 8, and string field theory exists.
Right.
And that's off-shell.
Yeah.
Maybe you're saying infinite number of fields.
Yeah. Right. So.
But that's not how it worked with it. Ashok was able to take this low energy limit without an infinite number. Loga has something to say.
Yes.
No, I don't remember, but I do think, you know, like it had an infinite number of things. I don't remember whether it decouples in the supergravity limit or not.
No, but yeah, see, you know, there always was this off-shell formulation of 2B theory by Sorokin and company with an infinite number of fields. But Ashok's thing was special because it wasn't that. Just if you go to the 2B supergravity limit, it just had a finite number of fields. It had the weird feature that it had a free scalar that decoupled from everything, you know, including gravity, which is really weird. But it came with a finite number of fields, I believe, in the low energy limit.
Yeah, I think that this previous work, they had problems in dealing with this self-dual form field, right? Or I thought that is what this additional degree of freedom did for Ashok. But yeah, maybe I don't remember very well.
Even I can't remember. Yeah, okay, I can't remember, but okay, yeah.
Yeah, I mean, so far I have not seen any good way off-shell formulation of supergravity, and I think Bernard had some argument why you need to introduce infinite number of higher spin fields, for example, I think in any good way if you want to make off-shell formulation. So that was, I think, one of the problems as far as I understand.
But just to say again, these arguments often come with assumptions, right? Which can, yeah.
Okay, so this is one of the reasons why we were interested in to complete the story of with n equal to 4. It was still hanging around for almost 3 decades. There's challenges. So what was known were the following. Of course, Weyl multiplet was known, and their supersymmetric transformation was also known. The linearized action was known, because at a linearized level, this Weyl multiplet you can write as a chiral superfield, and again the same sort of chiral density formula you can write on for n equal to 4, but that's at linearized level. So that was known in this paper from 1981, and of course Debu had a paper where he coupled n equal to 4 superangles with conformal supergravity, and so that was also known in 1985. But apart from that, nothing much was known till in 2012, where Buchbinder, Redknapp and Seidlin, they tried to obtain the n equal to 4 conformal supergravity action in a slightly indirect way, and they called it induced n equal to 4 conformal supergravity. So basically what they did is they took the n equal to 4 superangles coupled to conformal supergravity from the Deru's paper, and they integrated out the superangles fields and computed the divergent part of the quantum effective action, and they argued that this divergent part is 1 root xi,
divergences, it was local.
Yeah.
Right. Yeah. So that's how they obtain the Bosonian part of the input for supergravity action. And yeah. So then, so we were already working on this, and we thought that okay, they have obtained the Bosonian part of the supergravity action. So we already had a formalism, and we just had to work it out to say that okay, now we'll get the full, including the Fermi part, and that will also give us a way to check whether what they have obtained is right or wrong. And what we did is we developed a strategy to actually iteratively, it was a direct method where we know the supersymmetric transformation, and from there we apply the supersymmetric transformation, construct the action. It was a constructive method. We didn't have this chiral density formula sort of thing with us, so we started from the supersymmetric transformation to build up the action directly from scratch. And it was an iterative procedure. And
Iterating in what?
iterating means you just in the number of fields. So first we so there were various layers of iteration. First we start from a bosonic like term in the action which doesn't contain any gravity, no, and then we from there we iterate and obtain terms containing one gravity, no, two gravity, no, and containing having quadratic fields. The number of fields is 2. We don't count the number of fields inside the covariant derivative. Then we go and complete the cubic terms and quartic terms and so on. So it was like that. So yeah, again, it was yeah. So here there was one layer containing 0 gravity, no. Then this contained 1 gravity, no. Then this contains 2 gravity. Yeah, so we start with yeah. So we had a linearized action because that was also found in the paper by Bernard in 81, and we just generalize the linearized action by turning each derivative into a partial derivative into a covariant derivative, and that was our starting point. And from that we just impose supersymmetry. So we had a quadratic action here. So linearized action was quadratic. So we impose supersymmetry to find the quadratic terms in each of these layers. Once I have all the quadratic terms in each of these layers, then I can go back and I can find the cubic terms in each of these layers and the quartic terms and so on.
And this procedure should terminate at some point?
Yeah, so it will terminate at some point, but we were interested in only getting up to quadratic in fermions. So we stopped here. Otherwise, this will go on till psi cube and psi 4. But it will terminate as psi 4 because of the reason that the space-time index of the gravity, should be completely antisymmetric. Yeah, so the space-time index of the gravity, sin y, sin k, sin rho k, sin sigma l, it has some bars somewhere. So this should be completely antisymmetric in u rho k. The reason was the following, because under supersymmetry, this psi mu goes to d mu epsilon. And if I do an integration by parts, this d mu will come and hit one of these gravity node. And if only if it is antisymmetric in mu and nu, I can write this as a curvature. And bunch of other gravity nodes and other gauge fields. So that is the only way I can cancel the supersymmetric transformation. Only if it is antisymmetric in mu and nu. So that's also some argument from superspace which Dan Weber told us, but I don't understand that. But I understand it in this way. So the gravity nodes has to be totally antisymmetric in all its space-time index. That is why this terminates as sin 4.
That's like gamma 5.
Yeah, right. So this is how we obtained terms of the quadratic fermions, and it also included the bosonic part. But of course, we didn't expect it, but it turned out that we had a discrepancy with the results of Cyclin, Binder, and Bletnev. But upon careful examination, it turned out that it was the mismatch was due to some mistake in the paper. It was not a technical mistake. They had an oversight of calculation, so they missed some terms in the calculation, and once we take it into account, we actually get a matching. So,
Here also you have to modify the algebraic state.
no. The Weyl multiplet is given. The algebra is known. The Weyl multiplet and how the algebra closes is known. We don't modify the supersymmetric transformation. That's the whole point of doing off-shell formulation. Is once and all you fix your supersymmetric transformation and field content, then you are done. Unlike on-shell formulation, where you add some higher derivative terms, then your supersymmetric transformation also changes at every order in higher derivative terms. In off-shell formulation, you have everything is fixed. You don't calculate supersymmetric transformation.
So
Yeah.
Sir, so probably technical question. Is it easier to start with the psi to the power 4 term and then go down? Or?
Yes, that is what we will do in next. Yeah, for what we did in the earlier work, it was because this was our starting point. The linear interaction that was known to us was at the psi 0 order. So there we developed a strategy where we go from psi 0 onwards. But now I'm going to talk about a different way where we'll generalize the action that we have constructed. And there we actually follow the reverse path. We start from psi 4 and go up. Yeah, so that's what I will talk about. Yeah, so this, so the now question that we asked is, the action that we had in our paper was a supersymmetrization of the Weyl square term. Okay. The question we asked is, can we obtain a more general class of Lagrangians with non-linear coupling with a scalar, which is something of this sort. Okay. So here in n equal to 4 Weyl multiplet, we have scalars. We don't need to go to a vector multiplet or anything for the scalars. The n equal to 4 Weyl multiplet already comes with a scalar. Okay. And so the question that we asked is whether we can have a non-trivial coupling with the scalars. Okay. But as we can see, once we have this coupling with the scalars, this is going to break my SL2C symmetry. The SE11 symmetry is going to be broken. Okay. Because the only SE11 invariant combination of the scalar field that I can write down is phi alpha, which is 1. If I want to have a non-trivial scalar coupling here, that's going to break my SU11 invariance, which was there in this action, for example. Okay. But then why are we interested in this? It's because of certain motivation coming from string theory, where we see this non-trivial scalar coupling to be coming. For example, if you take type 2A compactified on K3 plus T2, there is a Weyl square term which is multiplied with modular function, and that's also supported by the microscopic degeneration formula obtained for dynamic BPS black holes, given by digraph in the Weyl, but also David Capelli or David Ashok in the CHL papers. And also this paper by Bindusar Sahoo and Steller, where they had written down some Poincare n equal to 4 Poincare supergravity action with curvature squared invariant. They also, they didn't write down the full action, I suppose. They wrote it in a very obscure form, but they had also this non-trivial scalar interaction. So, this sort of motivation to explain that there should exist a more general class of n equal to 4 conformal supergravity action with this non-trivial interaction with the scalar fields. Okay, so that was one of the reasons why we were interested in generalizing that thing. And the strategy was to build a n equal to 4 density formula, which is different from what we did earlier, where it was a constructive method of constructing the action. So here we were interested in building a generic n equal to 4 density formula, much in line with the n equal to 2 density formula, where which gives so n equal to 2 density formula was in terms of the chiral multiplet, but here we don't assume anything like that. We don't assume the density formula to be built out of a chiral multiplet. We just build a density formula in terms of some composite object, and then in the end, the row and the work would be to find these composites in terms of the n equal to 4 Weyl multiplet and get the invariant action. That is what was done for n equal to 2 also. It was in terms of chiral multiplet, and then you just find the chiral multiplet in terms of the Weyl multiplet fields and you get the action. So here we will obtain a density formula in terms of some composites, and in the end we will obtain the composites in terms of the Weyl multiplet fields and get the invariant action. Okay. So this was the idea, to build a generic density formula using the superform method. So our action is the integration of the fourth form, or if I write in terms of postural, it's RGT for x. Okay. And this J is a fourth form, and this is explicitly built out of the Weyl line and the gravity. schematically, I can break this up J into blocks according to the number of gravity nodes that they carry. So this is exactly what I put here. So there is one block containing 4 gravity nodes. There is one block containing 3 gravity nodes and 1 Weyl bind. There is another block containing 2 gravity nodes, 2 Weyl bind. There is 3 gravity nodes, 1 Weyl bind, and then only 4 Weyl binds. Okay. So this is schematically, I can break this 4 form into these 5 blocks.
The second last term was E cube psi, right?
Sorry, sorry. This is the E cube side. Yeah, the E cube side. Yeah. Right. Okay. So the idea is to start from the 4 gravity node form. Okay. And here we make some assumption. We will postulate. We will start with a simple form of this J psi 4. Okay, which is this. This is not the most general J psi 4 that I can write down. Okay. But this works, and although we have not proven any difference from this postulate, if we can take, which might also work, that will be different from our action by total derivative. There is some reason for that, although I don't know how to exactly state it here, but certainly this works. So this is a postulate where we start from this J psi 4, which contains terms like this. So here this Aijkl, Cijrs and C bar Rsij, these are in the 20 prime of SU4. 20 prime means they are antisymmetric in Ij and Kl, upper to index and lower to index, and traceless in any pair of index. So that is there in the 20 prime of SU4. They are Lorentz scalars. So that is one assumption, that they are Lorentz scalars. Okay. I don't have any gammas in between these psi bars and psi's. That's why they don't carry any Lorentz index, so they are Lorentz scalars. They could have carried some Lorentz index, but that's one assumption they're making. We start with this case where they are Lorentz scalars. And so those are the two assumptions, that they are in the 20 prime of SU4 and they are Lorentz scalars, so these are the composites. What is not an assumption is that they are also S invariant. S invariance comes because your whole action has to be S invariant. So each blocks has to be S invariant.
S is what, sorry?
S supersymmetry. That's an S, spatial supersymmetry. Yeah. So these are S invariant. Aijkl, Cijrs and C bar Rsij are S invariant. Yeah, so this is the starting point. Okay, so this is our postulate. We start from this point. And then, okay, so this is what I already told you. So these are also Weyl weight 2 because the overall Weyl weight has to be 4.
This last term also has an epsilon mu rho sigma.
Okay, yeah. So that's this one also has an epsilon mu rho sigma. Correct. Yeah. So these are in the 20 prime of SU4 and they have Weyl weight 2. They need to have Weyl weight 2 because the overall Weyl weight has to be 4. Overall Weyl weight has to be 0 actually. So this so this appears like this. So this Weyl weight has to be 0. So this is 2. So and this is minus 2. Psi bar mu y, psi mu y has minus half Weyl weight. So this is minus 2 from psi to power 4 and this is 2. So that is 0. Okay. So this has Weyl weight 2. It's a 20 prime of SU4 and Lorentz invariant. And they're also S invariant. S invariance comes because the whole action also has to be S invariant, which means that by the S transformation of psi, you know that each block has to be S invariant. Okay. So this is what.
Bindusar, just to interrupt.
Yeah.
At 2 o'clock we have a meeting to go for, so
Okay.
and we have to have lunch before that, so maybe 10 minutes.
Yeah, sure. Okay. Yeah. So this is the strategy part, so I can just rush through it. So this, basically then whatever Cijkl, Aijkl are, they are some composites. So they will, under supersymmetry, they will go to something like this. And this psi and omega, they will have projections. So this psi, where the m is low, so this will have projection on 60 bar and 20 bar of SU4, because epsilon upper m transforms in the 4 of SU4, so this will be the 20 prime cross 4 bar, and that will give you a 60 bar and 20 bar. And whereas the other ones, where the m appears up, those will have projections on 60 and 20 of SU4. Okay? So, yeah.
Wait,
so
sorry, the last thing was just take C and just decompose action of Q on it in terms of.
Right. This is the action of Q1. Yeah.
And just whatever its channels.
Right.
And given.
Yeah. Right. So that's what we have done. So this has projection on 60 bar and 20 bar and 60 and 20 of SU4. And now we want to look at SUSI variations containing 4 gravity no. SUSI variation of the full action containing 4 gravity no. So that will come from the supersymmetry transformation of this as well as supersymmetry transformation of this, because supersymmetry transformation of Weyl also gives us a gravity no. So that will come from this and this. So when we do that, so we'll get a bunch of constraints between the already defined composites, which will be this. So if we take the 60 bar projection of the xi and omega, that will be related to the A and C that appeared before in the 60 bar along with the lambda. Lambda is a Weyl multiplet field, and the 60 projection of this xi will be 0. So this constraint will come once you start cancelling supersymmetry variation of the full action containing 4 gravity. Okay. The other SU4 projection, which is the 20 and 20 bar of these objects, that will be related to the composites appearing in star J E psi. Yeah.
If you look at the supersymmetric transformation of psi, schematically, what do you get?
Oh, psi is so delta psi will be I. So there will be a dV epsilon I. There will be gamma dot d I j gamma mu ln j. Okay, the coefficients of that. Right. So gamma dot d I j means basically gamma a b like this, and there will be a psi bar I. Okay, there will be psi square lambda. I don't remember exactly what. There will be psi square lambda. There will be 2 psi and 1 lambda. Okay, so I don't remember exactly the structure.
That's right. I'm just trying to understand. You start with the 4 psi term, and you said the supersymmetry, and then you looked at terms in the supersymmetry variation that also gave you 4 psi.
4 psi. Yeah.
Where did those come from?
Okay, so see, so the star j psi q, star j psi 4 is this.
Yes.
Right. So the supersymmetry transformation from this, which contains also 4 gravity no, will happen when the supersymmetry transformation doesn't act on the gravity no.
But acts on the A's and the
C's. Yeah, exactly. And from the supersymmetry transformation of E psi q, which will give 4 gravity no, will happen when the supersymmetry transformation acts on the Weyl bind.
Weyl bind is E.
E. Yeah.
And also on psi, because you have
No.
psi square term here.
Yes. So psi cube, if you take one side, right. That will also
On the
come
square size.
Yeah. No. From here, from E psi cube, there will be one side which gives me psi square.
You are increasing
Right.
one side.
Right. So that will also come from one side.
But will not come from the terms where you act on. Now the variations of A, C, and so on, could those also have psi's in them?
No, they are covariant objects. So they don't go to psi. So this xi and omega. So under supersymmetry, the C and A goes to this xi and omega, which are also covariant objects, super covariant objects. There is no psi there. Right. So that is So you get this restriction on when you do that, and the other projections will be related to the composite that appears in the star J E psi q. Okay, that we saw how, because star J E psi q also gives you psi 4 variations, and the star J E psi q, for example, will appear like this, where so I have E is not, I am not written on E explicitly because I have absorbed my E into this canvas.
So yes, you said it, but I didn't understand that. You had a specific parametrization of the psi to the 4 terms.
Yes. Yeah.
Did you also give us a parametrization of the psi cube
No.
terms?
And it comes from that. So that is the only assumption we made at the psi 4 level, and after that everything follows.
Okay, so when you did this variation from the, given your parametrization of the psi to the 4 term, you use that to find the variation with psi.
Right.
But how could you work with the psi cube term if you didn't know the structure?
Yeah, so when we look at the variation of the psi 4 term, okay, so there we know how E varies, for example.
Right.
So when we we know that when we take the variation of the psi 4 term and take this 20 projection of that, we know exactly what type of cycle E psi cube term we should add to cancel this.
I see.
Right? So that is what we do. So yeah.
Sorry, Bindusar,
Yes.
may I ask a question? So in this previous slide, where you're doing this projection to 60, so this is just a statement that you're starting with psi to the power 4,
Yes.
and you have some variation for psi to the power 4.
Yes.
And there are certain variations which will cancel against the variations of E psi cube, but certain variations won't.
Won't, right, exactly.
And this is a statement that the variations which cannot be cancelled by the psi cube term should cancel within itself.
Within itself, yes, exactly. Yeah.
So this is so hence, like the 60 terms only involve the structure which occur in cycle number 4 because they better cancel themselves because they cannot be cancelled by
exactly.
psi cube.
Right. Yeah, exactly.
That's how you get it. So at this level you don't need to parameterize the psi cube because you just need to know what these projections cannot come from.
Right. And when you take the 20 bar and 20 projection of the same thing, you will see that you will have to add the psi cube E term, which will cancel them. And that should appear exactly in this way, and with the following relation. That the 20 bar projection of these objects should be related to this rho and rho 2 that I have written here in this particular way, where this rho hat is just some combination of rho 2 and the other composites. Yeah. So that's what you will get. Yeah. So that is.
So things which are orthogonal to these projections, there is nothing. So there is this projection onto the 20.
Right.
And so you have some constraints about that.
Yeah.
But the other components remain unfixed.
Yes. Right. So they are fixed, right? The 60 projections
From there.
from here, and the 20 projections are related to the lower composites. So the 60 projection of the earlier higher composites should satisfy this relation, and the 20 projection of this should be related to the psi cube E.
So that fixes it all.
So this is just one layer. Yeah.
I see.
Yeah. So then also we'll see that the S transformation of rho ijk and rho 2 ijk should satisfy this relation, and then it's a matter of one non-trivial consistency check that we are in the right direction should be to check the supersymmetry algebra, because the supersymmetry algebra we are not checking, we are not changing. So a non-trivial consistency check should be to check the supersymmetry algebra of this whole exercise, and that turns out to be all right. It needs the use of cadabra because it's extremely complicated to do by hand.
I didn't understand. Supersymmetry algebra is just an off-shell statement.
Yeah. So for example, we know delta q ofCijkl, okay, and then if I want to see whether the supersymmetry algebra delta S delta q onCijkl is the same as what I already know from my multiplet, right? So otherwise it will not be as consistent, right? So that we need to check, and that checking indeed comes out to be okay by the use of cadabra. So that is fine. Okay, so this is then this has to be continued by looking at supersymmetry transformation containing 3 gravity, no 2 gravity, and so on, which will give us some more constraints, and those constraints will not be an additional constraint. Those constraints will be guaranteed to satisfy as a result of the closure of Soucy algebra and the earlier first constraint. So the first constraint, this first constraint of the 60 bar projection that I wrote down, that is the only constraint I will have. Any other constraint that will follow in the later stages has to be satisfied as a result of the closure of Soucy algebra and this constraint. So that is one thing that I want to emphasize on. And then the other projections, other SU4 projections will give you the other forms, E square, psi square, E cube, psi, and so on. Okay, so I just again you can see this is just another layer of computation. But the idea is to start from that composite. We have this A, C, and C bar, and then the lower composites, the E cube psi, the E psi cube composite, that is given in terms of the object that is appearing in the Soucy transformation of C, A, and A bar. Then the other lower composite, E square, psi square, for example, that will be given in terms of the already known composites and their Soucy transformation, and so on. Right? So once you know this C, A, and A bar, then you know everything else. Right? So that is the whole idea of this invariant density formula. So the plan is to know this C, A, and A bar, which satisfies this constraint. This is the only constraint. Yes.
So it was A, C, and C bar.
A, C, and C bar. Yes. A, C, and C bar are the composites that appeared in starch psi 4, and they should satisfy this constraint. Okay. The psi and omega are the supersymmetric transformation of A and C bar. Right? So they should satisfy this constraint. Once you have this A, C, and C bar satisfying this constraint, then you have the entire invariant density formula. Okay. So that is So so the idea is the following: identify all possible S supersymmetric combination of the fields belonging to the Weyl multiplet, which are also Lorentz scalar, transforms in the 20 prime of SU4, and have Weyl by 2. Okay. So there are very few combinations that you can write out which satisfy this property from the Weyl multiplet fields. Okay. Right. So that is right, and then take arbitrarily linear combination of these finite number of combinations that you can write down which satisfy this property. They are and multiply them by arbitrary function of these quotient scalars, because quotient scalars are S invariant and they don't carry any SU4 representation. Okay, right? So, right, and then you solve this constraint. Okay. So you have made few terms which satisfy this first property, that they belong to the Lorentz scalar, belong to the 20 prime of SU4 and has Y by 2. And you take arbitrary linear combination of these terms, multiply them by arbitrary functions of the quotient scalars, and then solve those constraints. Okay. The result that comes out to be is that everything, there will be one total derivative which you can ignore, and everything else will be given in terms of one holomorphic function that is homogeneous of 0 degree and this associated Kähler potential, which satisfies this. The dependence on the Kähler potential can also be removed by plugging out a total derivative part. And then in the end, everything will depend only on this holomorphic function. Okay. And that is how we get our final action. This is only the bosonic. Part of the full action that we could write down. Okay. And this everything depends on only one single holomorphic function of the quotient scalars. So this is our generalization of the action that we obtained earlier. And but the nice thing is that if we set this constant to 1, this function to a constant, this holomorphic function to a constant, we recover our earlier action.
So now this is exact.
Yeah.
This has not omitted anything.
Yeah, this has not omitted anything. So that is.
Sorry,
Yeah.
so curly D is derivative with respect to phi alpha?
Yeah, this is what I defined here. Yeah. The curly D is here.
Oh, okay, alright.
And indirect is
For
here.
phi alpha?
Yeah.
So you are breaking the SU11 symmetry?
Yeah, here the SU11 symmetry is broken because of this presence of this H.
But if H is constant, it's
H is, if an H is constant, we recover our earlier action with SU11. So yeah, so this is some future directions, couple of future directions, where we can couple this thing to vector multiplet and get Poincare supergravity. Of course, that will be on shell because the vector multiplet is not off shell. And then you can use the above result to calculate high derivative correction to the entropy of n equal to 4 black holes, which was so far done in n equal to 2 settings. The supergravity aspects of the black holes that was studied was only where you are only using n equal to 2 supergravity action. This opens up the possibility of using the n equal to 4 supergravity action in studying these black holes.
so this might allow you to do some localization kind of calculations.
Localization kind of calculations can be done, but we need a vector multiplet, and the vector multiplet is on shell. But I talked with Samir, and he was saying that you don't need full off-shell supersymmetry to do localization. Even if one supersymmetry you can realize off-shell, you can still do localization. That is how he treated hypermultiplet also. So it's possible still. Thank you.
ICGS questions?
No, there are no further questions.
Kulaba? So, sorry, so the actions that you've constructed appear in what particular context? The black hole counting one.
Okay, so the action that we have constructed is still conformal supergravity action. It's not Poincare supergravity, but we can always add this action to our vector multiplet part and obtain, like then do the gauge fixing with the vector multiplet, and then we'll obtain Poincare supergravity action.
And sorry, just
Yeah.
out of this ignorance, what is the physical compactification that it will?
Oh, okay. So any okay, so type 2A compactifier of K3 plus T2 is a
besides localization application, what other application can you have in
Studying anomalies and divergences, because so that's the type of high derivative invariant that you can write down in Poincare supergravity. So that part I'm not very sure, but one can have some applications in studying the anomalies and divergences of n equal to 4 supergravity. So actually, basically, this Bindusar Sahoo and Staley, this paper that I will talk in the motivation part, they wrote down the Poincare supergravity. I think the scalar interaction that they thought would be there, I think, was by demanding some anomalies to be not there, or some loop or something. I don't know. This is something I don't know. Yeah,
But I thought for anomalies, your Lagrangian. So what I mean is that why is offshell important for calculating anomalies?
So n equal to 4 conformal supergravity is some statement about anomalies and divergences, which I am not sure. I am not studied that part, but there is some statement about anomalies and divergences in n equal to 4 Poincare supergravity. Yeah. This Bindusar Sahoo and Staley, this paper, I am not read that completely.
Yeah, the question that, like how the various anomalies are related, for example, how the conformal anomalies are related to the U1, SU4 anomaly, SU4 cube anomaly, is that the point is that you want to say how what are the constraints on the superconformal algebra on how the various correlators are related. Then various test sets and correlators are related, then you couple to some background gravity and you try to encode the test sensor correlators like some effective gravity action. Is that the point?
I'm not sure. Yes, right.
Sorry, just one more thing I'll bring up again. I've said this many times, but do you think that this kind of stuff can make contact with string field theory? Suppose you look at string field theory in the background of interest, like say K3 next. That's an off-shell formulation. This is an off-shell formulation.
Right. Oh, you're saying, yeah, right. So if it's an off-shell formulation, maybe there will be some, because the type 2A compactifier and K3 plus T2, just you write down type 2A, that is not off-shell. So
The ordinary string.
Ordinary string
theory.
String
String field theory on that should be off-shell.
Off-shell, yes.
Could it be that you're marrying these two ways of thinking give you deeper insight into structures? Is it the same way? If you take what string field theory does, go down below and does it do exactly what you've done, or is it something different?